There are two different laws that dictate the properties of thermal radiation. These are Veen's law and then the Stefan-Boltzmann law. So we're going to talk about those in a couple different videos. The first topic is going to be Veen's law. So if you look at the thermal radiation that's coming off from some object, so on the horizontal axis, this is going to be plot versus wavelength, lambda, and on this axis, I'm going to be a little fuzzy about this. I'm just going to call it energy. It's actually energy per unit time, energy per unit time per unit area. I'm not so concerned about that. And then the distribution of how energy is coming out at different wavelengths is going to go up, have some peak, and come down. The whole area underneath the curve, that is coming from the Stefan-Boltzmann law. So I add up all the energy for all the different wavelengths. That is Stefan-Boltzmann law. What we're concerned about here is how can we locate the point in that thermal spectrum where the most energy is coming out at. So the wavelength where it is brightest. That's the peak wavelength or the maximum wavelength. That is dictated by Veen's law. Veen's law tells us that the peak in that thermal spectrum is inversely proportional to the temperature, and this constant B is 2.90 times 10 to the 6th nanometer times Kelvin over the temperature of the surface, which then has to be in Kelvin. So we'll talk a little bit about temperature scales. You get weather from internet or on your phone. It's often going to be in terms of a temperature in Fahrenheit. Most of the world uses Celsius, and in the Celsius scale, it's tied to the properties of water. So water freezes at 0 Celsius, water turns to a vapor at 100 Celsius, and so that's the basis for the Celsius temperature scale. In physics and astronomy, we're going to use a temperature scale that's related to Celsius but a little bit different, which is the Kelvin scale. And the Kelvin for a unit of temperature is advantageous because there is no such thing as a negative temperature in Kelvin. You'd certainly have days in the winter where it's going to be below freezing, or in the Fahrenheit scale, well below freezing, so you can have a negative temperature. That screws up mathematical formulas. Like square root of a negative temperature is something going to give you an imaginary number, which is bad juju. So we're going to use a temperature scale where the smallest temperature that can possibly be is 0, absolute 0. There is no temperature lower than that. And then, therefore, all of the temperatures that you could measure, observe, record are positive. The Kelvin scale is related to the Celsius scale. The size of a degree is the same in both systems, so a degree Celsius change is just as big as a degree Kelvin change, but you're taking the Celsius temperature and shifting it by 273, and that makes there be no negative temperatures. So absolute 0 in Kelvin is 0. In Celsius, it's minus 273. All right. All right, so back to what all this is. Lambda max is going to be where this spectral energy curve is peaking at. Temperature is the temperature in Kelvin. and then B is this constant, 2.90 times 10 to the 6th nanometer Kelvin. So let's try a couple examples. Where do you peak as a thermal radiator? Your temperature is about 310 Kelvin. So your lambda max, I've got 2.90 times 10 to the 6th nanometer times Kelvin over 310 Kelvin. And the Kelvins cancel out, so we're left with a wavelength in nanometers, which is going to give you a round number for near infrared, near ultraviolet, and the visible part of the spectrum. So that's why it was set to take that value. That works out to be 9.35 times 10 to the 3 nanometer. And just a few little conversions for you. That would be 9.35 micrometer. Oftentimes we'll just shorten that to just call it a micron, so 9.35 microns. And then if you want that in our normal base unit for length, 9.35 times 10 to the minus 6th meters. So almost 10 to the minus 5 meters. That puts the light that you're emitting squarely in the infrared. Right? You don't see thermal radiation coming off from your own body or another person across the room from you. You can't see infrared light. But you are radiating energy to cool off because your temperature is above absolute zero, and you are going to be absorbing infrared light from all of the objects around you. All right, let's try another example. Lambda max for a particular star, and this is Bellatrix. This is a nice white-blue star in the constellation Orion. Surface temperature for Bellatrix is 21,500 Kelvin. So let's see where its thermal spectrum is going to peak at. So we'll have lambda max 2.90 times 10 to the 6th nanometer times Kelvin over 2.15 times 10 to the 4th Kelvin. And our units are going to work out. Kelvin cancels Kelvin. And that gives us 135 nanometers, which that is a shorter wavelength than even violet colored light. So this is outside the visible, and it's more violet than violet, so that is ultraviolet. It's like this is more red than red, so it's infrared. 135 nanometers is going to give us a color that is more violet than violet, and that is the ultraviolet part of the electromagnetic spectrum.